Hello everybody. In the last lecture we have seen that how the use of half wave and full wave rectifiers are done, and the rectifiers are nothing but the electronic circuits which converts the AC into DC. But unfortunately, for most of the cases the output of a rectifier is not a pure DC but is mixed up with AC components which are called ripple. So ripple are the AC components which are generally mixed up inside the DC, mixed in DC output of rectifiers. Now our idea is we need to remove out as much as possible all these ripples. So before going into that, first let us check the quality of rectification by the rectifiers. So in this lecture we will see the quality of rectification by the rectifiers in terms of some factors. Amongst all factors, we will be discussing here about ripple factor denoted by gamma. Before going into the derivation of ripple factor, let us see how to find the average or DC value of load or output voltage. The output voltage in a rectifier circuit is not perfectly steady as we have seen, but it is a time dependent periodic function because of those ripples. Now the quality of rectification is determined by the DC component of this periodic function. So if we denote by V0 the instantaneous output voltage of the rectifier, then average or DC value of load current will be given by IDC, it is VDC because we are deriving voltage. VDC at the output of the rectifier, the calculation will be 0 integration 0 to 2 pi. Why 2 pi? Because you know the one time period of a sinusoidal signal is 2 pi. So 0 to 2 pi VO, output voltage of rectifier, d omega t divided by integration 0 to 2 pi d omega t. So this division is by this term is because we are getting the average out of this calculation. So if we integrate the denominator, we should get 1 by 2 pi and the numerator only, integration 0 to 2 pi VO d omega t. So this is the average or DC output voltage of any rectifier. This is the basic fundamental formula. So here the omega is called, the angular frequency of the input AC voltage. This is angular frequency of input AC voltage. Now if we analyze, higher the value of this VDC will indicate the performance of the rectifier is better. Now let us go into, so this is the average, this is how to find the average or DC value of uh, the output of a rectifier. Now let us find how ripple factor is calculated. So it is denoted by gamma. I have already told you. This ripple factor is conceptualized from the fact that the output current of the output current or voltage of a rectifier contains a steady part, which is given by this equation if we consider it as a voltage. Now I have already told you, ideally there is no rectifier whose output is purely DC, but it is superimposed with periodically fluctuating AC components, owing to which the conversion of an alternating current into an unidirectional steady current by the rectifier is imperfect. So because of this imperfection, and to measure it, these fluctuating components, we have conceptualized this ripple factor denoted by gamma. It is defined as gamma is equal to, this is the definition, root mean square. In short, it is called RMS. RMS, value of the alternating components, value of the alternating components of the load voltage or current, divided by average value of the load voltage or current. So what we are seeing here, that ripple factor gamma is nothing but a ratio, so it is dimensionless, it has no unit. Now if empirically we express, it can be written as ripple factor gamma I or V RMS dash divided by I DC or V DC. So this is nothing but the empirical form of expressing ripple factor, where these terms IRMS dashed and VRMS dashed, these are called the RMS values. These are RMS values of AC components of AC components, because you know from your basic idea about electrical circuits that if there is any AC component, the measurement is done by its RMS values. So V dash RMS or I dash RMS are RMS values of AC components of output or load or output voltage and current respectively. And the VDC is the VDC or IDC is, obviously we have seen that the average or DC load voltage or and current respectively. So we can write, if RL is the load resistance connected with the rectifier, then VDC is equal to IDC into RL, we can write, and also VRMS dash is equal to IRMS dash into RL. Now if we consider IL is the instantaneous total load current, instantaneous total load current. If we consider this, the instantaneous AC component, this is the instantaneous total load current, or we can say the instantaneous AC component of the load current is given by of the load current is given by I dash is equal to IL minus IDC. So how this is obtained? This is obtained by, this is the total current through the load, and this is the DC part. So if we subtract the DC part from the total current, we should get the AC part. This is AC part or AC component of the instantaneous load current. Now the RMS value of the AC component of the load current is, therefore RMS value of the AC component of the load current we need to find is IRMS dash, because for ripple factor we need to find this one. The expression for RMS value is root mean square. So we have to keep all the three operations inside this: root, mean and square. So 0 to 2 pi, once again it is a periodic function taken at the input of the rectifier, periodic signal, IL minus IDC, because we have this term, we are taking this term, we are doing the we are considering the instantaneous AC component and finding its RMS value. So that's why this is the instantaneous AC component. So if this is the component, so we have to find the RMS value based on this expression. So this is IL minus IDC whole square d omega t, this is my signal, divided by 0 to 2 pi integration d omega t. That means we are just averaging this one. This is square, this is root, and bracket is closed. To the power half means this is the mean, this is the root. So this is square, this is mean, this term means square, this term means mean, and this term means root. That's why root mean square RMS. So this is the expression. So now this is equal to 1 by 2 pi integration, because we have integrated this and 1 by 2 pi is outside the integration area. So this is 0 to 2 pi, this term will remain IL minus IDC whole square d omega t whole to the power half. So now let eliminate the whole square part. IL square minus 2 IL IDC plus IDC square d omega t whole to the power half. Now if we analyze this expression, the first term of the integral, that means this term IL square, represents the effective or RMS value. This is alternately called effective or RMS value squared of the total load current. So this is the load current or output current, we can say. This load current or output current is taken as squared. That means load current squared. So since this is integration 0 to 2 pi IL squared d omega t, that means we have taken the RMS value or effective value of the total load current taken as a square. This first term is indicating that. That means this IL square is nothing but IRMS square, because this is the actual RMS value, because IL is the instantaneous load current. We have initially assumed that when we have started this derivation from where at the beginning we have considered that IL is the instantaneous AC component of load current. So this IL will indicate IRMS, and IL square means it is IRMS squared. The second term, that is this term 2IL IC, is actually 2 IDC squared. This is 2 IDC square. Why 2 IDC square? Because one thing I have written wrong. This is IDC. One IDC is here. That means IL from here we can say, if this is to be written as 2 IDC square, that means IL is nothing but my IDC. Now let us revert back the first expression of IDC. We had written there, just remember a little while earlier, that IDC is 1 by 2 pi integration 0 to 2 pi IL d omega t. So if you compare this one with this one, here it is 1 by 2 pi integration 0 to 2 pi like this. Take the second term of this integral, IL IDC d omega t. Now if you leave apart 2 IDC, this term, if you consider only IL d omega t, IL d omega t is there. So if this IL d omega t is matches with this IL d omega t, that means 1 by 2 pi integration 0 to 2 pi IL d omega t is giving us IDC. So this second, inside this integral, if we resolve the second part of this integral, we should get IDC. So if we put that value over here along with this minus 2 IDC, we should get 2 IDC minus 2 IDC square, resolving the second term. Okay, and the third term will remain as it is, plus IDC square. So we should be writing here this IRMS dash. So this equation will now become IRMS dash is equal to IL square 1 by 2 pi integration 0 to 2 pi IL square d omega t is nothing but IRMS square. So we should be writing IRMS square. We have already seen. The second term will become minus 2 IDC square after resolving the second term, and in the third term it is only integration d omega t, because IDC square is a constant, and integration d omega t is meant by only this plus IDC square, because 0 to 2 pi integration 0 to 2 pi d omega t means it is 2 pi, and that 2 pi, this 2 pi cancels out, so it remains a 1 only, so IDC square will remain over here, and this whole resolution of this whole integral will give us this expression, and this will be kept under this square root. Okay, so now resolving this, what we can write? IRMS square minus IDC square whole to the power half. Now by definition of ripple factor, that is gamma is equal to IRMS dash by IDC. We have seen just a little while earlier. So now substitute from here. IRMS dash, we have found this one, IRMS square minus IDC square whole to the power half divided by IDC. Or alternately, in terms of voltage, we can write VRMS square minus VDC square whole to the power half divided by VDC, where IRMS square is 0 to 2 pi integration IL square d omega t 1 by 2 pi. And VRMS then will be RL, load resistance, into IRMS. We can calculate voltage from here also. Now, so the gamma should be VRMS by VDC whole square minus 1 whole to the power half. So this is my expression for ripple factor. Now lower the value of this gamma, better is the performance of the rectifier. So for better performance, by rectifier, gamma should be as lower as possible. Okay, now let us see what should be the values for different rectifiers, the value of ripple factor. So case 1, half wave rectifier. In half wave rectifier, you already know that for positive half cycles of the input voltage, the load current IL is V divided by RF plus RL, where RL is the load resistance and RF is the forward resistance of the diode, because you know the diode is made up of semiconductors, and each of the semiconductor blocks, that is p type and n type blocks, will be having a finite resistance. So combining those, every diode will be having, if it is non-ideal, will be having some amount of resistance, and the resistance that is posed to the current conduction during the forward bias is called forward resistance, and RF is the forward resistance. So RF is the forward resistance because of bulk semiconductor. Inside the diode. that is made up, that with which the diode is made up of. So now this V, this is the applied voltage, this is equal to, we can say, if this is called the primary voltage, transformer primary, so Vs, that is the transformer secondary voltage, sine omega t, if we consider the input voltage as sinusoidal, divided by Rf plus RL. Alternatively, we can write it as Im sine omega t, because this term Vs by Rf plus RL, V by R, you know it is current I, and Im means it is the maximum value of, or the peak value of current. Im is the peak value of secondary current, transformer secondary current, or input current, you can say, secondary current. So where we should write Im equal to Vs by Rf plus RL, and this is the current that is actually the peak value of diode current, we can say also, or diode current, transformer secondary current that is flown through the diode in forward bias. During the negative half cycle of the input voltage, we will obviously see this IL is equal to 0 for negative half cycle, and this will be, this expression is for positive half cycle of operation. So from basic fundamental relation of to find the average value or DC value of voltage or current, we should be writing IDC equal to, for half wave rectifier, 1 by 2 pi integration 0 to 2 pi, sorry, integration 0 to pi, not 2 pi, because we are now segregating the 2 pi into two halves, 0 to pi and pi to 2 pi. In half wave rectifier, between the period 0 to pi, the diode is conducting, between pi to 2 pi, the diode is not conducting. So from 0 to pi, the signal is conducting, so we should be writing this Im sine omega t, d omega t, and from pi to 2 pi, 1 by 2 pi outside, it is 0 because IL is 0, so no conduction by the diode. So if we now, this is 0, so from here what we should get, we should be getting 1 by 2 pi into Im sine omega t integration, that is, you know, minus cos 2 pi minus, sorry, cos pi, not 2 pi, cos pi minus cos 0, and this is 0. So now into 1 by m, this cos 0 means 1 and this cos pi means 1. So 1, this is minus 1, cos pi means minus 1, minus cos 0 means 1. So this one, so that means this is minus 2 and plus 2, so that plus 2 and this 2 cancels out, so this is Im by pi. So what is IDC for half wave rectifier? Im by pi. So VDC should be Vm by pi. Now, so DC value is calculated. Now let us calculate the RMS value. So also IRMS So for gamma we need RMS value as well, 1 by 2 pi integration 0 to 2 pi IL square d omega t whole to the power half. This was the formula to find RMS, that is equal to 1 by 2 pi 0 to pi, this IL means Im square sine square omega t d omega t whole to the power half, and the other part is 0 because from pi to 2 pi there is no conduction by the half wave rectifier. So if we now calculate this, what we should get, 1 by 2 pi Im square by 2 pi, and this is sine square omega t. So integration 0 to pi 2 sine square omega t, so divided by 2, so 2 into 2 pi 2 sine square omega t d omega t whole to the power half. So this can be written as Im square by 4 pi, this 0 to pi 2 sine square omega t means 1 minus cos 2 omega t d omega t whole to the power half. Okay, so now if we again calculate Im square by 4 pi integration 0 to pi d omega t minus 0 to pi cos 2 omega t d omega t whole to the power half. So calculate further, Im square by 4 pi, what is this? This is pi minus cos 2 omega t, integration cos 2 omega t, that means sine 2 omega t, that means 2 pi minus sine 0 this one. So this is equal to Im square by 4 pi minus Im square by 4 pi pi minus sine 2 pi. So this is pi, this side is 0 and whole to the power half. So this should be IRMS equal to Im square by 4 pi into pi whole to the power half. So that is equal to, this pi cancels out, Im square by 4 whole to the power half, that means it is Im by 2. So IRMS is Im by 2 and therefore VRMS is Vm by 2. Therefore, IRMS by IDC we need to find is, just substitute Im by 2 and Im by pi. So this is pi by 2 or 1.57. So now ripple factor gamma IRMS by IDC square minus 1 whole to the power half, that is 1.57 square minus 1 whole to the power half, which is 1.21. So ripple factor for half wave rectifier is 1.21. So you need to remember and as well as need to practice the calculation of finding this value of ripple factor for half wave rectifier. Now let us find for full wave, case 2. For full wave rectifier, in a full wave rectifier, the load current flows in both the half cycles of the input signal, you know already. So IDC in this case, you know, 2 by 2 pi. Why 2? Because 1 by 2 pi is for half wave and 2 by 2 pi is for full wave. It is flowing for the whole of input signal cycle. That's why it's 2. This 2 is taken, and rest of the signal is same as it was for half wave rectifier. So if you calculate this, 1 by pi, rather Im by pi we should write, and here it is integration 0 to pi sine. So minus sine pi minus sine 0 sorry, this is sine, this is cos, not sine, this is cos. So this is cos pi minus cos 0. So this one will be Im by pi minus cos pi, means this is minus 1 minus cos 0 means this is 1. So this is minus 2. So this is plus 2, that means 2 Im by pi. So this is IDC for full wave rectifier, or we can say VDC is also 2 Vm by pi, where M denotes the peak value of voltage or current. And similarly we need to find IRMS, which is once again 2 by 2 pi integration 0 to pi. Why integration 0 to pi? Because we have taken it for half wave and we are just doubling it to get the full wave by multiplying the half wave expression with 2 to get the full wave from half wave rectifier expression. So similarly for RMS value, Im square sine square omega t d omega t whole to the power half. So if we now calculate once again like the previous one, 1 by 2 pi, what did we get from here? Take Im square outside, integration 0 to pi 2 sine square omega t d omega t whole to the power half, and here another 2 will come in the denominator. So this is Im square by 2 pi integration this one 1 minus cos 2 omega t d omega t whole to the power half. So from here we should write Im square by 2 pi. One is d omega t, that is pi minus integration 0 to pi cos omega t, cos 2 omega t, that means sine 2 pi minus sine 0, bracket closed, whole to the power half. So this is equal to Im square by 2 pi minus sine 2 pi means it is 0, and this is also 0, so 0 minus 0, this is 0, pi minus 0 whole to the power half. So here pi cancels out, and this is ultimately Im by root 2. So IRMS is Im by root 2, this is the expression, or VRMS is Vm by root 2 for a full wave rectifier. So all these expressions are important for you to solve further numerical problems. Therefore, let us find IRMS by IDC. This is equal to Im by root 2 into pi by 2Im, that is equal to Im cancels out, pi by 2 root 2, that is approximately equal to 1.11. So if we now find the ripple factor, root over 1.11 whole square minus 1, that is 0.482. So ripple factor for full wave rectifier is 0.482. So if we now compare between the two, the ripple factor of half wave and full wave rectifier, we are getting that full wave rectifier is having a lesser ripple factor than a half wave rectifier. So let us have a comparison of what we have derived till now between the half wave and full wave rectifier. Half wave and full wave rectifier, we have seen that IDC for a full wave rectifier are twice that of half wave rectifier. IDC or VDC is half of full wave. Here we should write IDC or VDC is twice of half wave. So this is one of the comparisons. Another comparison is the ripple factor of full wave rectifier is also smaller ripple factor for full wave, higher ripple